I'm going to share my screen, and yeah, we're going to do kind of a hands-on. The next two sections are on using the GUI to do really basic things. So importing tomography samples, doing microstructural generations and basic filtering, exporting STLs, that kind of thing. I'm going to combine the two 15-minute sections into one kind of 30-minute section, and hopefully we'll have some time at the end. So as I mentioned before, this here will be kind of hands-on, so it might be useful for those who have the GUI installed to try to do what I'm doing or some version of what I'm doing at the same time. I'm going to share my screen. I don't know if you can see it. So I'm sharing basically a virtual machine that's running CentOS on my Mac. You can see it fine?
Yes.
Okay, yeah. Perfect. So the first thing, following the installation instructions that Federico mentioned, is to activate the Conda environment. So we use Conda in order to manage our environments, as Federico mentioned in the installation video. So when you open up a terminal, and after you've installed PuMA and you have a distribution of Conda running, be it Anaconda or Mini Conda or something else, you'll see here on the left, there's this base. What that means is that you're currently in the base environment for Conda. Now, what you'll want to do first is say Conda activate PuMA, assuming that you named your environment PuMA. And now you have this PuMA environment shown active here on the left. So once that's been done, now the path has been added to all the PuMA executables. So you can run, for example, if you wanted to run the testing suite, you can run PuMA X testing, and I won't actually run the whole thing, but you can list all the unit testing that we can do. If you wanted to run, basically just any of the PuMA executables are run now that the Conda environment is active. In order to launch the GUI, you run the command PuMA GUI, and you don't have to be in the directory. You can run this from anywhere. So once PuMA GUI is launched, then you see the GUI that appears here, and we'll really go through pretty much all the basic functionality in this. Now, I want to first mention quickly the basic storage of materials in PuMA. So materials are stored in a Cartesian grid. So it's stored in a Cartesian grid that has each value in the Cartesian grid in the three-dimensional matrix is some kind of identifier. It can be a grayscale value in the case of unsegmented images. It can also be an identifier of the material phase if your material is segmented. So it could be 0, 1, 2 if you have 3 different phases of your material. You can manipulate this as you want within the software. And we are using this three-dimensional matrix like this because this is typically the way that tomography comes naturally. So I'll just show an example of a tomography sample. Let's see, PuMA Workshop. Okay, so here's just an example of a typical tomography file. I'm going to import it into Fiji, which is an app that we use sometimes for some simple post-processing. And you can see here it's stored as an 8-bit image, and each value, the value is shown right here, each pixel has a value between 0 and 255. And this would be kind of what a raw tomography sample would look like, possibly after a little bit of filtering to try to sharpen the edges between them. Now, if you're doing your post-processing in Fiji and you want to upload it into the PuMA software, you should say save it as a 8-bit TIFF image. That's the file type that the PuMA GUI likes the most. So image type 8-bit, and then save it as a 3-dimensional TIFF. So file, save as TIFF. and then it saves it as a 3-dimensional TIFF. Once you have it in that 3D TIFF format and you want to import it into PuMA, you can click on the Import 3D TIFF button. You can say Import 3D TIFF, or you can just drag it directly onto the screen, and you have an image that looks very similar to what we saw in Fiji. You can scroll through the various slices here on the right. I want to briefly talk about using segmented versus unsegmented images. So I'll go through the basic thresholding-based segmentation process in PuMA in just a second. But first, I just want to talk about what a segmented versus an unsegmented image looks like. So this was stored as an 8-bit TIFF image. You can see down here on the bottom, we have the size of the image, 200 by 200 by 200, so X, Y, and Z. We have here on the right, the minimum and maximum value that's present in here. If we were to drag a segmented image on here instead, at first we're not seeing anything, but if we click this rescale, it'll now rescale to the minimum and maximum value in the domain. Since this is segmented now, that just becomes 0 and 1, and we can scroll through and we can see the segmented image. The next thing I want to mention is the voxel length. So the voxel length is each of these individual pixels, or in 3-dimensional voxels, has a physical length associated with it. If you're generating the material, then this is something that you specify in order to match the physics that you're interested in. If you have tomography samples, this will be an output of your settings for your tomography, and then as well as the actual any kind of post-processing or scaling that you've done on this. We have a question from Alex Martin. Do we have access to these files through the installed files? So if you download the source, the answer to that is yes. If you installed it using Conda, you can get these files here. If you go to github.com NASA PuMA, sorry, I should have specified this at the beginning. If you go into, I think it's Python.
It's inside PuMA Pi, sorry. Yeah.
Sorry,
if you go back, Python, PuMA Pi, and then data, the first one.
Okay, then here you go. You've got access to a number of different ones. The two that I'm using right now is this 200 fiberform.tiff and 200 fiberform segmented.tiff. So you can just download these directly from the GitHub. And it looks like Francesco is putting a link in the chat. Okay, so as I mentioned about the voxel length is kind of the physical length of the of a single voxel. So it defaults to 1 micron, which is, order of magnitude, usually about what a tomography sample is for the kind of materials that we're imaging. It can vary wildly depending on what you're doing. For this particular sample, the correct size is 1.3 microns. So you click on the little voxel length button, you can update it here, you say okay, and then that has been updated, and that's now associated with this file. So any material properties that you run, it will use this new voxel length in order to use that. Now I want to make a note on segmentation. So next we're going to talk about how to do simple threshold-based segmentation. So not all materials can be segmented easily. Not all tomography files can be segmented easily using a just thresholding-based process. So if you have a material, so for example, you can quite often have where the grayscales in this region here in a void could actually, even though the human eye can see the difference here between the two phases, it could be that some of the darker regions inside one of the phase, just from an artifact of the imaging, is actually darker than some of the lighter regions in one of the other phase. You can try to avoid some of that through filtering. There are some filters that try to preserve the edges so that you're not losing detail on your surface, but often filtering alone isn't enough. And you can use some more advanced techniques. Deep learning is just one of them in order to produce higher quality segmentations that you can then upload after you've segmented it into PuMA. But if you can use simple thresholding based segmentation, I'll show an example of that. So you click on this little threshold button here, and you have this that pops up. So this is a two-phase material, meaning we have just void, so air, and then we have solid. So because of that, you would expect this, which is a probability distribution of the grayscale values. So on X here is the grayscale value from 0 to 255, and then in Y is the frequency that that value occurs. And you would see that we have basically two peaks, ignoring the artifact from the imaging around 0. We have a peak around 60, which corresponds to the kind of mean value or most probable value in the void phase. And then we have another peak up here around 170, which is kind of the most probable value of the solid phase. So if you want to segment this into 0, 1, you would use the sliders here to choose the range that you're interested in, and all the values here are inclusive. So let's say we choose 0 to 89. And this obviously depends on what your material is. We've worked with this tomography sample a lot before, and it just turns out that in our case, 0 to 89 is a good value for the threshold for the void phase. And then you can set that value to whatever you want. So when you click apply, everything between this 0 and 89 range will be set to a new value of 0. So once you click apply, then that has been applied throughout the entire sample. And then we can do the same thing with the solid phase. So again, inclusive, so we go 90 to 255, and we set the new value to be 1, for example. We say apply, click the rescale visualization, and now you can see that we've generated a segmented image that if you compare it to the segmented image that we had before is the same thing. So the segmented image I loaded earlier is the exact same as the segmented image that we just produced. So I want to make a note about using segmented versus unsegmented images for some of our calculations on material properties. But actually first, I should pause here before moving into visualization and anything else. Gerardo says you're having problems with the scrolling bar. So if you click, it's not scrolling for you. If you don't mind my asking, what system are you using? And if you want to, it's scrolling but not showing change. What's the Ubuntu 20.04? And on the bottom, you're seeing a domain size that is something reasonable. Are you using this sample? Okay, so 200 by 200 by 1 means that in the Z direction, you only have one image, meaning that for some reason you are not importing a full three-dimensional image. So yeah, if we were to scale this to if we were to scale this to 0 to 1, then when we scroll through, we're not seeing any changes. Now we have 200, 201. So I think that the problem is with the image that you imported. But maybe during the next section or during break, we can offline talk about this, and I can try to help sort through what's going on there.
Can I just mention one quick thing? Maybe Gerardo saved it from Fiji, and so if you just do command save, for example, if you just do that one control save, then that saves only one slice. So that could be if the origin of that. you need to go and do save as and then TIFF. Yeah.
Okay, yeah, that's a good point. Okay, so move on to, Gerardo, you don't necessarily have to do the Fiji process. Did you download the image from the GitHub, the 200 fiber form? Okay, all right, well, we'll maybe talk offline and try to sort out what's going on with that one. But yeah, it seems like it's not registering it as a 3-dimensional TIFF. So I wanted to make a note about segmented versus unsegmented images, and why you would sometimes want to keep your data in an unsegmented format. So depending on the material property that you're calculating, sometimes PuMA is just using the, what material ID you are. So basically just zeros and ones, even if you run it on an unsegmented image. But other times, PuMA is actually creating a higher fidelity surface around the material, and it's using that higher fidelity surface in order to do, say, for our particle methods, for example, we do particle reflections and particle collisions based on the surface that we create. And when you create a surface based on a segmented image, there are some tricks to try to make it higher quality, but generally speaking, you've lost a lot of data. So I'll just show an example in visualizing. So in order to create a 3D visualization of this image here, if you click 3D render up here at the top, and we're going to render from 90 to 255 because we're selecting the range of the phase that we want to visualize. So we want to visualize the solid phase here, and it just happens to be for this tomography sample, as I mentioned earlier, that 90 to 255 is a good threshold range for this visualized sample. Now we're going to create a contour rendering here, and I'll just make a note quickly. I'm running this on CentOS. Yesterday, when I was preparing for this, I noticed that there is a very slight bug, which I fixed in my version, but has not been pushed yet on CentOS. It appears to be only on CentOS, where when you generate a rendering, the background is transparent. So I fixed it on my version, but if you're seeing a transparent version where the background is fully transparent instead of white or instead of gray, that's just, it's a small bug that only appears in CentOS, and we're going to push a fix to that soon. So this is what you see when you generate the contour rendering, and you can see it's only 200 cubed, but it actually has a pretty good fidelity representation of the surface. It's quite smooth around the individual fibers. Now, if we were to generate a rendering of, instead of the unsegmented image, if we were to do it with the segmented image, so I'm going to rescale it here. So now we just have zeros and ones, and I click 3D render. Now, importantly, this has changed. So now our solid phase is 1. So we want our solid phase to be between 1 and 1. Again, it's inclusive. If we wanted to visualize the void phase, we could visualize 0, 0. And we generate a contour rendering. And you can see that it's still capturing the material. You can still see the fibers, but everything is a lot clunkier. It's a lot bulkier. It's not able to produce a high quality surface representation of this. There are some tricks to kind of do a blur or a mean filter or something like that, which I can show an example of if you're interested in, that will let you, from segmented data, get a more clean looking surface. But even if you do that, all you're doing is blurring the segmented surface, so it looks smoother, but you've actually lost a lot of data. So anytime you are doing a surface triangulation on an unsegmented image with an appropriate threshold, you're going to get a better representation of what's happening at the surface. Let's see, moving on. So I'm going to move on next to generating materials, so generating artificial domains, but I'll just pause quickly to see if anyone has any questions. Again, just unmute yourself and ask, or type it in the chat. I'll wait a couple seconds, and then I'll move on to generating materials.
Hi, Joseph. This is Ali. I just have a quick question.
Sure.
So about that last topic where you're talking about not using the segmentation because of this averaging of pixels and non-smoothness of surfaces, what about samples that you cannot really threshold easily?
Yeah, so if you had a sample that you had to segment using some kind of external software like Dragonfly or something, then you're right. There's really no way that you can reproduce what I'm showing here. Now, there are tricks that you can do in order to generate a smoother visualization if you want. And just to be aware that when you're doing this, it's going to produce a smoother visualization, but you're not actually, you've not actually created a higher fidelity representation of the surface. You've just kind of blurred it. So it's good for generating images, but it's not actually giving you any more information. Now, here's a trick that you can do in order to do that. So you've imported a segmented image to 0 and 1. And now we can use this thresholding, and we can change this 1 up to some higher value. We can just kind of arbitrarily make it 255. So now it's still segmented, but we've changed our value range from 0 to 255. And then let's just put a blur. Let's just do a mean filter with a radius of, say, 2. And I'll get into filtering again in just a second. And you can see when I click preview on that, it's just kind of blurred all the edges. If we apply that to the entire image, then now if we do a 3D rendering, and in this case, we've gone from 0 to 255. So after the blur, half of that value, which is 128, is an appropriate threshold. And then you contour that.
I see.
Then you can see here, we actually have a very, very smooth visualization that's been generated. But the smoothness is just an artifact of that blur that we did. And you've probably ended up blurring out some features that may have actually been in the original material.
Yes. Yeah, that makes sense. It's good that there is a workaround in GUI in there.
Yeah,
Ali, one thing that is important also to mention here. I mean, of course, Joseph is focusing here on the visualization, right? But eventually the question comes to how important is this, like, for computing an effective material properties, right? So, and the answer is it depends, right? So there are some properties where this might be important, right? If it's based on the surface. There are some other properties where this is actually really negligible. Think about thermal conductivity. So hopefully during the next few tutorials, we'll sort of hint a little bit to it, but we can also have a separate conversation about this and go deeper. But it's an excellent question. Yeah.
Thank you.
So we have another question from Sujit. I'm sorry if I'm pronouncing that wrong. It appears that one other person is having an issue where the GUI is freezing in 12.0.1. I just checked. I am running 12.0.1 and I'm not having that issue. What I would recommend is to, if you used the Conda, Federico, if you disagree with me, please say something. But if you used initially the Conda installation procedure, I would recommend following the uninstallation procedure and then trying to install it again from source, which is also, I mean, that sounds scary, but it's still just one line. You just type and you just run an install script and it installs everything for you, and see if that fixes the problem. I am running on 12.0.1 right now, and it is not. It's working fine on my Mac as well. If you guys are still having issues, yeah, please put a bug report in the GitLab, and then also reach out to us, and we'll work with you to make sure it's working. Federico, do you have anything you want to add on that?
No, I think I would have recommended to do the same thing, and as you mentioned, like add like an issue, open an issue on GitHub, and hopefully we can replicate the error, which is easier to debug that way. But either way, we'll try to fix it.
So it's just worth mentioning that the code we released is just very recently been released open source. We've done as much testing as we possibly can on all of the various systems that we have access to. But now that more and more people are using the code, it's inevitable that people are going to have issues, but we're definitely very committed to sorting out these issues. So if you're having an issue, please reach out to us and we'll make sure that we resolve it quickly. We can even just set up a one-on-one video chat or something to make sure that the code is able to run on your machine.
Hi, Joseph. My name's Cameron. I have a quick question again about the blurring of the edges of the fibers.
Okay.
So why would you not prefer the sharpest contrast between? Could you explain again why you would not want the sharpest contrast between the fiber edge and then the void space?
When you say sharpest contrast, do you mean something like this?
Yes. Is it just because of the voxel size not being small enough? As you zoom out to like maybe 1,000 by 1,000 by 1,000, would you prefer to have this sharpness of the threshold?
No, it's not that. Let me see if I can annotate on my screen to try to explain why this is happening. So imagine you have So imagine you have a voxel that looks something like this. Can you guys see the annotation I just did?
Yeah.
Okay. And let's say it's segmented. So now you have a value of 0. So it's going to, when you're doing a triangulation, the values are not stored at the self centers, they're stored at the edges. So you've got, let's say 0, 0, 1, 1 here, which means that you're going to end up with a surface that cuts through the middle. So it's going to be right like that. And then let's say you have another configuration where, where you have, 0, 0, 0, 1. So now you're going to have something that cuts through like this. And really, that's all you're limited to. When you have zeros and ones and it tries to decide where the surface is always going to intersect at exactly the midpoint between them if there is a surface there at all. Whereas if you're using a continuous value, so if instead of 0 and 1, you're using you've got values here that are like 50 and 80, and you've got a threshold value of 79, then it's going to put that right here, and then you can create a little triangle there. So being able to place the triangles anywhere along, having the triangles intersect anywhere along the edge when you have more continuous values makes it where you can have a really smooth surface. Whereas if you were to generate that, if you've got a curve, for example, and you want to represent that curve in a grid, it's going to end up with things that are only 0 degrees, 45 degrees, and 90 degrees. So to show that again, PuMA Workshop. Here we go. So if we do a 3D render here, 1-to-1, you can see that all the triangles that are generated here are really limited in what angles they're able to be. They're able to be straight up, straight sideways, or at 45 degrees. And there's really nothing else because there's no extra data in there to inform a different angle. Whereas if you're running that on a unsegmented image, then it's able to it's able to produce a wider range of angles. And then you're able to get this much smoother looking surface. And if you're doing a blur on it, then you're basically just hacking that to try to create that smoothness somewhat artificially, but it still produces a smoother visualization. I don't know if that helps answer your question or not, but it
does. Thank you. Okay. Thank you so much.
I think I've actually gone a little bit over time already, so I'll be a little bit quick with the
So Joseph, yeah, we're running a little bit late, but I think we can take time, and you know, our schedule is inevitably going to shift by 15 minutes. So I think we're still okay.
Okay. Yeah, that's fine. I'll be a little bit quick on the domain generation. I won't monologue too much. So I'll just mention quickly the different types of domain generation that we're able to do. So the first is just generating simple primitive shapes, like a cylinder, for example. When you click on, you can click on the icons on the side. You can also say generate, and then the different options here. So I've just put some default values for the tutorial here. The first three options here, which you're going to see in all of these, are the domain size. So we're going to generate a domain that is 100 cubed. We next, in X, Y, and Z, need to assign a start point for the cylinder, and then we need to assign a direction vector for the cylinder. So the start point, again, we're using the C++ indexing, so starts from 0. So start point, direction vector, radius, length, all these values are in voxels, and you can assign whatever voxel length is appropriate after that. So you say generate, and we're going to create a cylinder. If we scroll through here, we can see it's in the Z direction, which is into the plane. And an important note that anytime you are generating a material, I've put a little note here, anytime you're generating a material, automatically 0 to 127 is considered void, 128 to 255 is considered solid. And the reason it's not just generated segmented to begin with is because the exact issue I was talking about before. You can segment it if you want. You can go through this threshold process and do whatever segmentation that you're interested in. But by default, we created unsegmented with 127 to 128 being the cutoff between the two phases. Now, I should also note that if you're using the GUI, all you can do is generate a shape or a material, or like random structures here, but you can't generate multi-phase materials. If you wanted to generate a multi-phase materials with different primitives of different values, different materials, and then run simulations on that, you have to use either the C++ version or the PuMA version, but directly from a script. So there's an example of that in the Python tutorials, which is called the multi-phase tutorial, that shows you how to generate a multi-phase material and then kind of how to run simulations on that multi-phase material using the Python. So if we visualize this cylinder, 128, 255 contour, you can see here we've generated a cylinder in the Z direction. So I'll show just very quickly, we can generate a sphere, same thing, X, Y, and Z size, sphere center point, radius, generate. If we scroll through here, we can see this sphere there right in the middle. Oh, that's not what I meant to click. If we then create a 3D render of this, you can see the sphere that we've generated. And again, since it's unsegmented, we're able to get this very, very smooth triangulation of the surface, even with a relatively small material. Moving on to some of the more complex microstructures, we can do random fiber generations. I won't get into all the various versions of random fibers we can do. The only one I'll mention right now is just generating fibers that are straight with a circular cross section. You can also generate fibers that are curved, And you can also generate fibers that have a non-circular cross-section with kind of like a flower-like shape with a center and then petals around, which is more representative of actual carbon fiber materials. But for this first example of just a random fiber generation, first thing, X, Y, and Z size, as with all the other generators, average length of the generated fibers, average radius of the generated fibers, plus or minus on either of these if you want. And then this is kind of the important part here, which is how much, the nomenclature here is a little bit confusing, but it's how much variability you want in the angles. So if you wanted a fully isotropic material, then you have 90, 90, 90. And that's just saying that the angle can vary between 0 and 90 degrees in each of these three directions. Probably we should change this to be a unit vector, so between 0 and 1, but for now it's between 0 and 90. So this would then generate a fully isotropic material. If we say generate, and it keeps generating fibers until it reaches this porosity value that you specify. And you can see here, we've generated that material. If we 3D render it, again, 128 to 255 since it's artificially generated. You can see this random fiber structure that we've generated. If you wanted it to be, say, a planar structure instead, so if you wanted no variation in the Z direction, you can set that to be 0. And if we generate the same material, 3D render, contour. Now you can see we've generated a planar structure. So in X and Y plane, there's a lot of variability. In the Z, there's none at all. We have a question about units. What units are used? So all of these parameters here are strictly in voxels. So if it's 200 voxels by 200 voxels, then that's what the units here are. In order to specify the actual units that you are using in the physical system when you calculate properties, you will vary this voxel length parameter down here. So if you wanted this to be, for example, 0.5 microns. So if you wanted to create, well, let's say you wanted to create a radius of 12 micrometers, which is pretty close to what a carbon fiber typically is. Then you would change your voxel length to 2e to the minus 6. And now your, actually, I think 5 is closer to what the radius, I think the diameter is about 10. But now we have a radius of 12 micron for each of these fibers. So that would be how you change the physical length of these. There's a similar structure that can be made for spheres, randomly generated spheres, intersecting versus non-intersecting, porosity, average radius, deviation of the radius. So if we generate this, you can see the sphere structure we've generated here. And I'll just show one last thing, which is called the triplet periodic minimal surface. Again, you specify your domain dimensions in X, Y, and Z. And then these parameters here, W and Q. So the triplet periodic minimal surface, you can Google it. There's a Wikipedia article on it, I think. It's a sinusoidal equation or a couple different equations you can use. And these W and Q are, so W is inside of the sinusoidal functions, Q is on the outside. Q roughly determines what the porosity is. It's not a direct one-to-one for the porosity, but you vary Q to vary the porosity, and you vary W to vary the length of the period for the sinusoidal function. So you can see what we've generated here is this sinusoidal shape. If we do a 3D rendering of it, you can see we've generated this foam-like structure. And these are useful because you can make them highly tailored and then you can 3D print them. So in my case, I was using this for some work on porous media burners, but they can be used for a variety of different applications. So I think that wraps up the section on doing basic generation, import, export, that kind of thing. I want to make just one last comment, which is many of you may be interested in outporting an STL so that you can visualize it in some other software. You can say export STL, or just click on this button right here, and it will create a watertight STL. You specify the material phase that you want to output, and you say export. It'll generate this watertight STL that you can then visualize in whatever visualization software you're interested in. So, question from Gerardo: does PuMA have Boolean operations like cylinder subtraction from created geometries? The answer to that is yes, but not in the GUI. So you can absolutely do that, but you would want to run, say, PuMA Pi, for example. Federico will show you how to set that up, and then you can do whatever operations you want in terms of subtracting, multiplying, whatever else. In the example for multiphase, it shows you a little bit how to do that. Okay, any other questions before we move on to the next section? I think we're a bit late on time anyway. Oh, sorry, somebody said something.
No, it was me. I just wanted to mention that I answered to Jose's question about whether on Windows we have access to the GUI, and no, the answer is no right now. But you will be able to follow the PuMA Pi tutorials that I will talk about later on Windows as well.
Okay, perfect. Well, I'll go ahead and stop sharing.
So Joseph, somebody pointed out to me in private that that on some of the topics we are going quite fast, right? So we'll try to slow down a few of the things, right? Anyway, all the workshops are being, again, the workshop is being recorded and all the sessions are being recorded. We'll try to post video also, so that after this event, you can take your time and go through.
It's also worth mentioning that we've recorded tutorial videos. They're not available yet, but they should be very soon. On each of these subjects that expand a little bit more. It's kind of a balancing act. I would love to take more time, but we could be here for 24 hours if we go too slowly. Yeah. But yeah, I'll try to slow down a little bit and explain what I'm doing in more detail.